the Reynolds average Navier-Stokes data actually. So the next this article which I show here is also by Tagizade et al. They also increase the accuracy of turbulence closure modeling using data-driven techniques. And this one by machine learning accelerated computational fluid dynamics by Koch Kov et al. Is particularly interesting because they also study two-dimensional turbulence, and they report around 80x speed up. And also they say that training Reynolds number can be small, but the testing Reynolds numbers, that is, they extrapolate in Reynolds numbers, higher Reynolds numbers, and they get accurate solutions. And this one by Kim and Lee is also a nice paper by a nice paper to study for the turbulence in a channel flow, and they use recurrent neural networks and generative adversarial network kind of combination to recreate solutions at testing Reynolds numbers which are not part of the training. And this article, recent one, editor suggestion by PRF by Narasimhan et al., where they have used kind of a machine learning classifier to distinguish the laminar and turbulent regions, and they post that the results are accurate than the wall resolved LES simulations. So next in this slide, I'm sure everybody knows these papers. So these are the papers which inspired us for our work, and this one by Rezi et al., which was a seminal work in 2019. And then after that, the hidden fluid mechanics, learning the velocity and pressure fields based on the passive scalars from the experiments. And it was also rigorously shown in this JFM article as well, as a flow espresso cup. And this article by Physics Informed Machine Learning, again in Nature Reviews, where they have also highlighted the limitations of PIN when it comes to multi-skill phenomena or multi-physics problems. So that is why then turbulence is always multi-scale phenomena. So how we can improve it is something which is an open question, and they have addressed, they have mentioned the XPINs idea to which can actually address such multi-scale phenomena. So, and there are papers which also look at pins for chaos and turbulence. And this work, NSF Nets, again by Professor Kannabiran and his group, looks at channel flow using pins. And the recent work by Didier Lecor and his team also looked at turbulent natural convection using pins. And also this exciting recent article which came out last month in Archive, we are still trying to understand this as well, respecting causality, causality based pins. So, and these are some of the articles where pin plus data is used, not only pin, plus some training data from the interior of the domain which was used. So this article, again, the Looker, they have also used some data from the interior of the domain. And this Wang et al. Paper was particularly interesting in International Journal of Heat and Mass Transfer, I think, where they study natural convection within an enclosure using PIN plus some minimal data from CFD. And also another recent paper where PIN plus data are used for blood flow by Azani et al. So next, okay, so now in this slide, I'm showing two-dimensional turbulence. That is the application of our PIN models. So why two-dimensional turbulence? The first thing is both myself and Kannabiran, we are interested in geophysical and astrophysical systems. And not only that, it is also simpler to study than a three-dimensional system. That is also another point. And the third point is it is also having this multi-scale phenomena. So, and if you want to address it using pins, it could also be extending to other multi-scale phenomena, I believe, in industrial systems where I come in. So to briefly tell about two-dimensional turbulence, so there is it has a property of dual cascades. So from intermediate scales, the energy is transferred to the large scale, and from the intermediate scales, entropy is transferred to the small scales. This was also introduced by the seminal paper of Robert Krishnan in initial ranges in two-dimensional turbulence back in 1967. And we also show here an article by Jason Lowry in 2014, where they have simulated very high Reynolds numbers of two-dimensional turbulence. For further two-dimensional turbulence information, one can also look at the review paper here in Annual Review of Fluid Mechanics by Bofetta and Akin. Okay, so next, so we want to study pins for two-dimensional turbulence. So some of the questions which we think it's important is whether pins can capture the statistical properties of the two-dimensional turbulence. And also, instead of focusing on the exact evolution, can we capture the overall statistical behavior of the flow? So we stick to a single GPU because of time constraints and also computational constraints. And with minimal data for training, can we predict the large scales and small scales properly? So it's pretty interesting when we talk about the results. So I'll next introduce the problem definition in rigorous mathematical terms. So this is the Navier-Stokes equations along with the divergence constraint. This is the governing equations. So we study a force dissipative turbulence in a two-dimensional domain with periodic boundary conditions, where nu is the kinematic viscosity, mu is the large-scale friction coefficient, yeah, due to confinement effects in third direction. And we also apply the Kolmogorov forcing. And the non-dimensional number which we have is the Reynolds number, which is u times the length scale divided by the kinematic viscosity. So the quantities of interest for us are the energy, entropy, and the kinetic energy spectra. So the energy is the area average of the velocity square, and the entropy is the area average of the vorticity square. So in two-dimensional turbulence, the conservation of both energy and entropy happens due to absence I mean, in three-dimensional turbulence, this conservation happens due to absence of forcing and dissipations. That's why we are important to look at both this energy and entropy.
Venkatesh, I have a question. So here the forcing is stationary. So you're talking about stationary flow, so you can use ergodicity and so on, right? Space-time. F is independent of time. So,
yes, no,
so you have a stationary flow. So therefore the averaging can be interpreted anyway, space or time, right?
Yeah, one can do that. Yeah, if one can do at a particular point, it's also there. But I think it's at the end of the day, for a large Reynolds number flow, even if the forcing is time dependent, I guess one can still use some ergodicity principle, because the flow in phase space is still supposed to be confined around this particular Reynolds number. If the forcing doesn't, the amplitude of the forcing function itself is well behaved, I expect that even for time periodic forcing or time dependent forcing, there might be an ergodicity even in that particular system.
Not necessarily, but we'll talk about
maybe.
That.
Yeah, maybe I'm wrong. Yeah, that's what I thought. Yeah, thank you.
Okay. So, okay, so I'll go to the next slide. Talking about the DNS simulations. So we use the Fourier pseudospectral methods for the numerical, that is our numerical method in space, and in time marching we use this implicit explicit ARS443 method. And this code is also validated with Gomez et al. In 2005. This is also running in GPU. And in the next slide, I'm showing that so the truth value for the validation of the the pin 1 and pin 2, which we'll be introducing, is at Reynolds number 4000, and the resolution was 5. It's actually 512 cross 512, and CFL is 0.005. And once the statistical steady state is reached, we take some training data from these two red vertical lines in time. So this is the region of interest for us, where we take the training data and the testing data. Okay, so now I'm going into the pin plus database model. So this is the schematic of our problem. And you can see this cuboid at the X, Y, and T and dimensions. The green surfaces are the testing times, and the red surfaces are the training times. And the pink star is the boundary points, and the triangles are the equation, and the circles are the data points. So we'll come to this again when we talk about the hyperparameter searches. Okay, so now I'm going into the architecture of the pin 1 model. So basically, pin 1 model is the same as the standard pin model, except that we have an additional loss calculated for the overall total loss, that is the L data loss. So we have inputs X, Y, T, and the outputs from the neural network is psi p, as the stream function pressure. Stream function because we want to constrain, I mean, divergence constraint has to be satisfied. So we have the output psi. And yeah, so we don't actually minimize the divergence constraint in the equation loss. Okay, and I'll go to the next slide. So here we have described the losses in a bit detailed way. So this is the initial loss, data loss, and boundary condition loss, which takes into account the periodicity of the boundaries. And this is the equation loss. And in the initial and data loss, the superscript E denotes the DNS data. Okay, so now coming to the interesting part. This is the pin 2 architecture which we have proposed. So it consists of the low wave number and the high wave number network. And it's similar to the pin 1. It's just that there is a difference here. The initial and data losses only are trained, uh, are minimized separately for the low and high wave numbers. So LINI consists of LINI L plus LINI H, and data also L data L plus L data H. So the motivation for this is so as you can see, this is the energy spectra. So we were having difficulty with pin 1, which we will come to, but so we were thinking, so we need to capture the average kinetic energy spectra properly, so that all scales are physically resolved, physically realistic and meaningful. Not only the accuracy is low, but also the large scales and small scales are captured properly. So here we had the idea of splitting the U by a simple Fourier transform into kx and ky space. And this yellow line, which is part of a circle, because kx square plus ky square is k square. So this is the low wave number U hat, and the red triangles the high wave number u, just for representative purposes. And when you do the inverse Fourier transform, one can get u low and u high. So now uh, the difference from the pin one is that the L in E again it's consisting of the low and high wave number losses, and the data as well, it consists of low and high wave number losses, and together the U which we finally get are still minimized. The losses are minimized for the boundary condition and equations. So this is the for us, this was the motivation. And next I'll go to the hyperparameter search. So as you can see in this table, so we tried out different sets of neurons, different sets of layers, and different training data as well. And for all these searches, we fix the initial points, boundary points, and equation points. Because we did try out different equation points and boundary points initially, and then due to computational constraints and also accuracy, we thought it's good enough to go. So we actually fixed these number of points, and it's also shown schematically here once again, so that it's clear for everyone what are these points. So the number of neurons and layers which we tried are also shown here. So I'll go to the results from which we found out optimal set of these hyperparameters. So here we show the loss versus the epochs, training epochs. So the top one is the top row is the pin 1 and the pin 2 losses for the different set of neurons, and the middle one is for the different set of layers, and the third one is the number of training data. So we found that the optimal set for pin 1 is the 400 neurons, 5 layers, and 0.1% training data. And pin 2 was 250 neurons, 250 250 in each layers, and it's 5 layers and 0.1% training data. Apart from this, we also want to remark here, this is using the in the losses, when you have seen the loss comprises of 4 quantities, initial data, boundary condition, and equation. For the equation loss, we did increase the coefficient because we thought that when we do that, we may get better physically realistic solution. So in this slide, I'm starting to show the results in comparison with DNS. It's pretty interesting comparison of pin 1 optimal model and pin 2 optimal model when we increase the lambda 4 in the loss. So the loss also I've written it below once again, just to be clear. So you can see we have just increased the lambda 4 value from 1 to 150 in both pin 1 and pin 2. So the errors are increasing with respect to lambda 4, but it dips at some point. Again, it keeps increasing. So the large value in RMSE versus lambda 4 can also, I mean, is also possible because of the errors being a root mean square of the total errors in the entire flow domain, and mostly it comprises of the large scales. So,
excuse me.
Yeah.
Hello. This is Lulu from Japan. I have one question here. I'm a little bit not sure about your setup. Do you solve for forward problem or inverse problem, or you assume you are solving for forward problem but with extra data measurements?
So you're asking if it's a forward or inverse problem, is it?
Yeah. Yes.
Yeah, this is a forward problem, and we are comparing it with the DNS solution.
Yeah, but you also
So
have the second to the data term.
Pardon?
You also have the data loss.
Yes.
So which is not a standard for forward problem. So you
okay. Yes, I agree. It's kind of learning from data, you can assume, but then if you if you go back to the PIN paper in 2019, so the second part is the data-driven discovery, where you have lambda in front of the Navier-Stokes, and you using data, you try to find out what is a lambda. But we don't go to that. But then we use some data to see if we can give a good enough prediction for from using pins.
I think so. This is like a hybrid, because you use, in the training, you use some data, right?
Yes.
In the test from the DNS. In the testing, you still use data, the data term, or not?
In the testing, no. In the testing, there is no data.
But in the training, you use some DNS data.
Yes, training data is there, but in the testing, it's completely is predicted by weights which are already trained by using the. So in the testing times, it is totally the average spectra testing times does not contain any data. So
but this is, but for PIN, you can only solve for one condition. So the testing is just a solution for that specific condition.
I didn't understand. Can you come again?
So basically, I'm a little bit confused. So for this hybrid training, this is useful in which scenario?
Can you go back to that plot that you had, the slices, the green and the red? I think that will make it.
Yes.
Clear. Yeah, right here.
Okay. Okay. So,
Sorry,
can you repeat the question?
So I think what you're doing, you're testing at different times, right? Unseen times.
Yes.
You're comparing statistics. You will be comparing statistics, or you're comparing statistics for time intervals which you have not used, right?
Yes, exactly. Yes.
And
so
no
the data points, yeah, I hope it answers the question. Because the testing times does not contain any of this data. The green surfaces does not comprise any data. So it is purely predicted by the PIN model.
Okay, I see.
And, yeah, and we compare it with the DNS.
So Lulu, it's the answer to your question is at different times. He wants to see if he can track the statistics at different times.
Yeah.
Yes. Yeah, but ideally, if we can train the PIN perfectly without any data, we should be able to do it, right? Ideal case.
Yeah. Yes.
Okay, I see.
But
okay,
hybrid training is good even for deep net. We know that. So.
Okay. Shall I proceed?
Venkatesh, this is Amaya from Brown. I have one question.
Okay. Yes.
So can you go to the next slide? Okay. Here the loss function for the different training data. So as you increases the training data, it is obvious that the loss will decrease slowly compared to less training data, right? And in the optimal state, you are actually choosing the smallest amount of training data.
Yeah.
So that doesn't make any sense. Either you plot the error, relative L2 error, and how it behaves with increasing the training data. It's obvious that.
Okay. So yeah, I get your question. So actually, when we did that, we also saw in comparison with DNS, we didn't show it here. We see that for the at the testing spaces, the errors were kind of increasing when we increase the training data. So it is trying to kind of overfit maybe. So that is something which we saw. That's why we stuck to 0.1%.
But
also due to time constraints, we stopped it.
So this training data, does it contain noise, or it's the DNS data you're using?
It's a DNS data.
But then why your error is increasing with increasing the data? And that's not clear.
Yeah, that's we're also like looking at it.
So, but I think maybe if I can answer, is just that we compared lost data. There are like a lot more points at which lost data is computed. So I do not know if it's the best. We do not normalize with the number of points. So maybe I do not know whether it's a correct way of comparing. Maybe I'm thinking it's a different losses by definition. So I do not know whether we can directly compare the values.
No, that's why I asked whether there is an error in the data or not. So
No, I think we should have ideally normalized it with the number of points at which we are computing this data loss, which we haven't done. We just, I think if can you go back? Maybe, yeah, I do not remember now. Venkatesh, can you just go back? No, maybe we don't do some normalization. No, even earlier. Yeah, here, the definitions. Oh yeah, we do kind of normalize. Can you come down? The definitions of L. Oh yeah, so maybe there was not this slide actually. So pin 1 loss, I think. Yeah, so we do divided by n data.
In data, yeah.
Yeah, so it's good question. Maybe yeah, we don't know actually. So that is something that we have to check. Yeah,
No,
thanks for
yeah, I think if I remember correctly, there was some increase in error, but we thought the lower the
we had
number of
definitely issues with overfitting. So at testing time, it was performing very badly, whereas at training times it was performing better.
going very good. Yeah.
Yeah. So maybe
it was.
yeah. So maybe there is
We'll
some
take another look at it.
Yeah. So maybe there's some issue at testing times where the losses were increased, were like much higher than the case where we used lesser data. Maybe that is what I would answer no, but we will have to look at it again.
Okay.
Yeah.
Thank you. Thank you.
Okay, so yeah, so coming back to this slide. So as you can see, the energy spectra at the bottom row. So you have for pin 1 and different lambda 4 values. So the large scales and the small scales are not captured properly for the spectra. This is the average spectra at the testing times. That is the only on the green surfaces. And on the right side, we have the pin 2 with different lambda 4 values. So it was getting better as we increased the lambda 4, and at lambda 475 we thought, okay, this is the optimal solution. So we took the best pin 1 and lambda 4 combination, and also the best pin 2 lambda 4 combination. We went ahead and compared the other important quantities like the energy time series, entropy time series, and the energy spectra. So we found that the pin 2 is performing much better than the pin 1, and considering that we have used only 0.1% of the total DS training as training. Yeah, so this is the main result of this work that is shown on the right side. This is energy spectra, which is having quite a good agreement with the DNS till 10⁻�8 or 9. I'll go to the next slide. So in this slide, we're showing a small video of the evolution of U and V with this in comparison with the DNS from pin 2's best model. So on maybe I'll run it again. So as you can see, the evolution of large scales and small scales are kind of large scales are pretty good. Small scales are also there, but whenever there are some shear in the flow, there is where some errors are cropping up. So that is something which we plan to address. We are addressing currently. We are looking at it. So okay, so I'll now go to the next slide. So these are some of the large scale statistics which I've shown here. These are the stream function in the Fourier space. So yes, hello. Am I audible?
Yeah, you are audible.
Okay,
Joseph, Joseph, you may, yeah, it's okay, it's muted. You continue.
Yeah, no, sorry.
okay. So these are the large scale statistics. So here we show the Fourier space stream function psi11, psi1, and psi33. So these represent the large scale flow structures. And as you can see that the PIN2 and DNS, they compare very well. And as you go to psi33, there are slight deviations, and that is starting to creep up, but the overall statistical evolution is captured. And if you go to smaller and smaller scales, that is when the DNS comparison fails. So at least for the large scale and some small scales, we are still, we are actually successful in capturing the statistical evolution. So in conclusion, from this study is we are able to capture the large scale structures evolutions, and also the energy distributions up to 9 decades is captured. Even though the exact evolution of DNS is not there, but fluctuation amplitudes are of the same order. And very importantly, the applications of this is the storage and retrieval of time of solutions at very small time steps. Basically, meaning if there is a very high resolution TNS simulation, and in space and time, obviously, if it's a very fine mesh simulation, and you are constrained by very and the time steps and the storage as well. So in these cases, we can take minimal data, and then we can actually reconstruct large scale structures using such techniques, using PIN especially, and then recover the solutions. So this is one important application of this work. And secondly, one can actually study reversals of large scale modes in turbulent flows, which is applied to the astrophysical and atmospheric systems. And also the PIN2 type architecture from this work can be used in multi-scale physical systems, especially in industrial scenario where you have defects, and people also do molecular simulations where it's all multi-scale, and at least I potentially see that this could be used in those multi-scale physical systems in the industrial scenario. So for the future work, we still have to address some of the deviations from the DNS solutions, and whether we can reduce the amount of data which we are used for training. Also improving the optimization of the hyperparameters, and also to increase the Reynolds number and speed up the training multi-GPU codes. These are something which we have in mind. And also possible solutions to be explored are the adaptive loss functions, and explore ideas based on this recent nice article on causality based PINs. And yeah, that's about it. And we also want to acknowledge the CAPDP deep learning platform team from Robert Bosch in Germany. So they had provided us the GPUs, and also the supercomputing platform Param Shakti from IIT Kharagpur. There also we had run some of our simulations. And thank you all, and thanks a lot for the organizers of the Crunch group, Professor Kannabiran, for inviting us, and Dr. Goswami as well. Thank you. And any questions, please?
Venkatesh, you didn't tell us about the cutoff wave number.
Okay, the cutoff wave number. Yes.
That should be some dependence on that. Your inertia range was not that big.
Yes.
So, but how do you know where to cut it, and what is?
Yes.
Because there's other ways to deal with this multi-scale nature. There's several papers now.
Yes.
Yes.
So the cutoff wave number we chose was k equal to 10 for this particular work. So we fixed k equal to 10 and then we proceeded. But we are looking at other cutoff wave numbers at present actually.
So if you look at, okay, so that explains actually if you look at the right, there's a discrepancy between the DNS from wave number 10 to about whatever that is, 20, I think. Yeah, there's a discrepancy, and that's probably because of that separation.
Cutoff wave number.
Because you know the wave numbers talk to each other.
Okay.
So then eventually the small scales will be independent of this, but and you catch up with that. But so did you vary that? Did you vary the?
We varied it. Yeah, we varied it from 10, 20, and 30. So the one which was at 10 did the best. So
yeah. So we didn't put it up in the in this talk, but we have results on 10, 20, and 30, and 10 performed the best. So we stuck to 10, and then we proceeded with the.
We think it might depend on, because right now we are forcing at k equal to 4, so there's a constant injection of energy at 4. So that is why we thought like it should not be too close to the forcing scale, because then it might have issues with how does the energy is injected into the system. So we just chose some values on 10, somewhere in between, and then we proceeded to check for other values. It didn't give much difference, so we decided to stick with 10. So, but a real study wasn't done actually for different, like systematic study wasn't done.
Yeah, a possible improvement for the periodic boundary conditions is to impose them exactly. I hear you penalize.
We found it later. Yeah, that is.
Yeah, so the paper by Steve Dong, my former postdoc, is at Purdue, and so he has a paper where he shows you how to do it exactly. Yeah.
Okay. Yeah, we'll note it down.
Yeah, so that is something we also want to check, so that we can go up to all the way to viscous scales.
Yeah, so that is something which is quite interesting.
Yeah. And Professor Kannabiran, could you please, because you mentioned that comment on ergodicity, so if you could just let us know which.
Yeah, so you cannot, like, if you have even a jet flow is not a stationary flow, so you cannot really use. There's something called weak ergodicity hypothesis that you can do, but it's more like ensemble averaging over windows of time, and that's how you do it, but not.
I see. So you're thinking about other examples, not periodic boundary conditions.
Well, the thing is here, what you're doing is you are in a stationary regime, and one thing is the averaging, the other one is the extrapolation. How would you, even for a turbulence in the wake of a flow past the cylinder, which is limit cycle, it will be difficult to actually extrapolate. But certainly, if you don't have any time scale, will be difficult to extrapolate or to interpolate like you between, because you have non-stationary flows. So I bet that if you use a time-dependent forcing, it depends on the frequency, of course. That will make it difficult to do what you're doing. So that will be the ultimate test, actually.
I see. Okay, thank you. We'll try that also. With you are suggesting a time periodic or a random in time force?
Well, random in time is very difficult. If it's totally random, you'll go back to what you are. But maybe some
periodic time force.
Yeah.
Okay.
I have more questions for the speakers. So if there are no more questions, thank you.
I saw somebody. Matthias is asking a question.
Yes,
if I may, so I have two short questions. Yes. So the first one, I didn't really get how you, which data you are using. So is this a real measurement, or is this artificially generated? I mean, I'm asking because I know researchers that are using photos for turbulent flow.
Okay. Okay. To answer that, we have performed the DNS direct numerical simulations using another code, and that we are choosing is for training.
So using two different codes.
Yes, for one is separately
you
one
could
pin.
also think about the lattice Boltzmann codes.
Okay. Yeah, but
so a completely different method.
Yeah, I mean, since we are using this Fourier spectral pseudospectral method that could resolve all the scales, so we thought we'll stick to that as the truth values.
Yeah. Okay.
Yeah.
And maybe a second short question. If you come from the physics side, then of course you know that the turbulence in 2D and 3D is completely different. I mean, different scales, and I mean due to the vorticity and so on.
Yes.
So, and if I look on your method, I think there are no obstacles to extend this from 2D to 3D. I mean, are there any problems to do this in 3D?
So far, we haven't tried out 3D, but it's definitely on the cards. We would definitely want to try out 3D in the future. We don't see a particular constraint as of now. We would definitely try out want to try out 3D in the future. Yes.
But you will see more fine structure in the turbulence.
Yes.
In
yes.
3D.
So probably more challenges. So more excitement.
Okay. Thanks.
Yeah.
So Matthias is talking about vorticity stretching for those of you who are not,
yes,
who are fluid challenged.
Yeah.
I'm talking about some data. Some data is a mechanics person, not a fluids person. So.
Yeah, in fact, I'm a techno-mathematician, so I'm somehow in between the subjects.
Thank you very much, Venkatesh, for taking the time today, and Kannabiran, thanks. Keep up the good work. Yeah.
Yeah. Thanks a lot, Professor. Thanks a lot, everybody.
Thank you for having us.
Yeah.
Thank you, everyone. With this, we move to our second speaker.
Okay.
Maybe you could stop sharing, Dr. Venkatesh.
Yeah.
Sicheng. Sicheng, if you're there, could you start sharing your screen?
Okay. Can everyone hear me?
Yes, we can hear you.
Okay. Please wait a minute. So can everyone see my screen?
Yeah, just give me a second. I'll just introduce you.
Okay.
So our second speaker is one of our team members. He would be talking about graph representation learning in hyperbolic space. And he's a first-year PhD student at Crunch. And you may want to start.
Okay. So today I'm going to give a brief introduction of this topic called a graph representation in hyperbolic space. And it seems a very big title, but let's first decompose it into three parts. The first part is graph. The second is representation learning, and the last one is hyperbolic space. So first, I'll briefly introduce graph and machine learning tasks on graphs, and then introduce some necessarily mathematics prerequisite knowledge, which consists of some basic notions in Riemannian geometry and some properties of hyperbolic geometry, which is our focus in this presentation. Then I'll explain the connections of graph and hyperbolic geometry. That means why do we need to use hyperbolic space to do graph representation learning? And at last, some algorithms based on these observations. So first, machine learning of graphs. Graphs are universal data structures used to describe relational data. And in a graph, because graph is consists of some nodes or vertices and potential edges between them. In a graph, the nodes represent different objects, and the edge represent relationships between them. For example, this is a social network, and every node here, that is every image here, we can view them as for example, as a Facebook account, and there's a link between them if one account follows another. And the second figure is just math geology, and there's a link between two mathematicians if perhaps one advise another, and this should be a directed graph. The third one is a molecular, and we can view atoms as nodes, and two atoms are connected only if there are some chemical bonds between them. The last, just the internet. In fact, this is a visualization of the well-known algorithm called PageRank. It is the algorithm that Google used to give a score to different webs and assign a score to it and decide which should appear first in your Google search. And of course, there's a hyperlink between webs. And so these account for the edge in the internet graph. And in graph representation learning, our goal is to find a low-dimensional continuous representation of graphs that preserve the graph information. And usually we compute one embedding per node, which is called the node embeddings. And we will use these in some downstream machine learning tasks. So what is representation learning? Like a good claim that a good embedding should preserve the similarities between objects as well. I'll give a few simple examples. For example, in a natural language processing task, we map different words to a Latin space via a word embedding function f. That means we are doing something like word to vec. Then the f mother and f mom in the Latin space should be very small, because the mother and mom, these two objects are very similar in the word space, so they should be also similar in the Latin space. Also, such as cat and bread, their similarity should vary. They should have not very because they are dissimilar, so their distance in the Latin space should be big. And something interesting is that the difference of vectors also makes sense here. For example, f man minus f woman, this should approximately equals to f king minus f queen. And this is in NLP. If we are speaking of graphs, so in graph embedding tasks, the similarities of the image of two vectors should be small if v1 and v2 are close. And how to define close here is up to us. For example, we can define v1 and v2 are close if they are adjacent to each other. That means they are connected by an edge. Or we can say they are close if v2 is within the two-hop neighborhood of v1 and something like that. So in practical settings, we can say if two users have many friends in common in a social network, then a good representation should preserve this information by making the node representation very similar in the embedding space. So the common use the similarity functions in S is the inner product and the distance function. And we'll talk about that later. And in fact, in most cases, the Latin space S is just the standard Euclidean space that everyone was familiar with. But also there are some many choices, such as the hyperbolic space we're going to talk about. And there are also some more, for example, take the probability distributions as the Latin space to capture the uncertainty of that embedding. And this is a general framework for representation learning, write it mathematically formally. So our input is a graph, consists of vertices and edges, and the embedding space S. The encoder is a parameterized map from node V to its node embedding. And in the simplest way, the encoder is just an embedding lookup. That means we pre-compute the embedding, and when we want to use it, just find the corresponding embedding and use it for downstream tasks. The decoder is a mapping from the embedding to the similarity score. And our objective is to optimize the parameter of the encoder to maximize the similarity for node pairs that are similar. And our output is the node embeddings. Applications, that means downstream tasks, for example, node classification or link prediction or graph classification. Just to clarify that here we are, I'm running 3 different tasks because node classification are at the node level. That means we can just input the embedding of that corresponding node you want to classify. And the link prediction is at the edge level. That means you need to concatenate or aggregate two node embeddings together for a downstream task. Well, graph classification is at graph level, and you need to aggregate all the node embeddings in a graph. The next, I'll give some brief review on geometry, especially in Riemannian geometry.
Hello, Sicheng.
Yeah.
Yeah, I have a few questions. You run too fast a little bit. So
okay.
So the similarity function here is the larger the similar or the smaller the similar, the SIM function.
It should be the larger the similar.
Okay, I see. Also, then why the mapping from the embedding to the similarity score, we call it as decoder.
In fact, we call, yeah, I know what you mean, but in fact, it's just like we use it as a convention to call it encoder and decoder because that's a pair, right? But in fact, we don't use kind of this decodering applications. It's not like, for example, in auto encoder, we have an encoder and have a decoder, and we need. I mean, when we are training for that embedding, the decoder is only useful when we construct loss functions.
Okay, I see. Okay, thank you.
So this because we do not have any level. This is completely self-supervised.
Yeah, got it.
Okay. So next, I'm going to talk about some preliminaries in geometry, and this part might seem a little bit abstract, but I won't make everything mathematically rigorous. I just want to introduce the high concept. And yeah, first, a manifold is a topological space that is locally Euclidean. The manifold, we can just think of that generalization of a surface in a high-dimensional space. What does it mean by locally Euclidean? Because to define a topological space, we need to define a collection of open subsets. And the locally Euclidean means for every open subset of this topological space, we can find a map that maps this open subset to a flat Euclidean space. And in fact, that map is called a coordinate chart. And a very simple example is just think of the Earth. Because everyone knows that Earth is a sphere and the surface of Earth is not flat, right? But we can represent the surface of the Earth using a two-dimensional map. And the map, because everyone uses maps to travel from one place to another, so it means that it can represent the local regions of the surface of the Earth. But in fact, it is the surface of the Earth is not Euclidean, but the map is in a two-dimensional Euclidean space. Then a differentiable manifold or a smooth manifold is a topological manifold with globally defined differential structure. Because many times people want to do calculus on manifold, so we need to have a differentiable structure on it. And in many cases, that leads to a very important concept called tangent space. The tangent space is just like the analog of imagine a tangent line to a curve on a two-dimensional space, and this figure just illustrates this. It illustrates this idea. For example, M is a manifold, and we want to, and the TXM here is the corresponding tangent space. In fact, M is a two-dimensional manifold, and it's here is in three-dimensional Euclidean space, and the TXM here is just a two-dimensional plane. It can also be seen as a hyperplane. So informally, we can just think of it as it's an n-dimensional vector space approximating M around P at first order. And a very important property is that the tangent space is Euclidean, and it has the same dimension of the as the manifold has. Then let's talk about Riemannian manifold. It's a very important collection of manifold. A Riemannian manifold is a real smooth manifold M equipped with a positive definite inner product GP on the tangent space TPM at each point P. That means for every P, we can construct a tangent space TPM here, and GP is defined on every tangent space. This is called Riemannian metric. In fact, if you have the same manifold M here and you equip it with different Riemannian matrix, that leads to different Riemannian, totally different Riemannian manifold. And there's also some important concepts. For example, the geodesic. The geodesic is just a curve with shortest length. This is analogy to the straight line in Euclidean space, because we all know if we in a standard Euclidean space we have 2 points and the straight line has the shortest length. But in non-Euclidean geometry, this doesn't hold. We can have a curved line that has the shortest length, because the length or say distance here, they are related to Riemannian metric here, and the Riemannian metric can be very complicated, and so the straight line doesn't have the shortest length. So these are also two very important concepts. First is the exponential map and logarithm map. These two is just like we define a map between the tangent space and the manifold. The exponential map, in fact, it allows us to locally carry the Euclidean structure of the tangent space to the differential manifold. And the logarithm map is just the inverse of the exponential map. In fact, this can be generalized into the relations of Lie group and Lie algebra, while a Lie algebra can be seen as derivatives of a Lie group, and the exponential map, we can use an exponential map to map from a Lie algebra to a Lie group, and the vice versa. So, but here also and the last two concepts. The first is the parallel transport. It's not that trivial like in the Euclidean space. It's defined as a map from one tangent space to another tangent space that carries a vector in the original tangent space along the geodesics from a point to another. And the curvature is just a mathematical quantity that describes how a manifold deviates from being flat. In fact, there are many different definitions of a curvature. For example, everyone is familiar with the scalar curvature with respect to a two-dimensional surface. But in fact, in higher dimensions, especially in Riemannian geometry, the curvature has several different definitions that their meaning also differs a lot, like Ricci curvature, Gaussian curvature, or something. And in this presentation, we are focused on sectional curvature. In fact, we only need to know that it describes how a manifold deviates from being flat. Very large curvature means it's twisted a lot, something like that. And so let's step into non-Euclidean geometry. Yeah, because Euclidean geometry is based on the 5 postulates of by Euclidean, and in fact, the first 4 of them are very, very like simple and obvious. But the last one, it means a parallel. It's the parallel postulate. It says that for any given point, not on a given line, there is exactly one line through the point that does not meet the given line. That everyone should know that this is called parallel line. But in fact, mathematicians have worked for centuries to try to prove that can we discard that? Because, for example, can we use the first 4 postulates to derive the 5th one? But it ended up in failure. We cannot prove it. So there are also some mathematicians like Gauss. They think of, can we just throw away this 5th one, and can we just get some non-Euclidean geometry? And in fact, it works. Here's are some characteristic properties of three different geometry. The first one is Euclidean, and the second one is the spherical, and the last one is what we are focusing on. It's called the hyperbolic geometry. And their intrinsic distinction in that the parallel lines in Euclidean space is 1, and in spherical is 0, and in hyperbolic space in the infinity. That leads to many different properties of these 3 kind of geometry. For example, in curvature, in Euclidean space, the curvature is 0, and on spherical space is greater than 0, while in hyperbolic space is less than 0. And their triangles have different shapes. Like this is a thick one, and this is a thin one, and the sum of angles and triangles are totally different. Also, the formula to compute length and area also differ a lot. But we can see something interesting here because in spherical and hyperbolic space, for example, the circle length here, this is a sine function, and while in hyperbolic space, here this becomes a hypersine. And while correspondingly in the disk area, the spherical disk have the area here. The formula is cosine, and while this is hypercosine. So this is kind of interesting. And so let's see what's our main role here is the hyperbolic space. This definition is the hyperbolic space of dimension n is the uniquely simply connected n-dimensional Riemannian manifold of constant sectional curvature equals to -1. So while we are talking about hyperbolic geometry, hyperbolic geometry only requires the curvature to be less than 0, but the hyperbolic space is it has a constant sectional curvature equals to -1. And so in fact, all we are talking about is very like abstract, and we don't have some intuitions about what a hyperbolic spaces look like. In fact, by the celebrated Nash-Whitney embedding theorem, we know that every Riemannian manifold can be isometrically embedded into some Euclidean space. So if we want to embed the hyperbolic space into Euclidean space, we can have something called hyperbolic model. That means we represent the hyperbolic space in a Euclidean way. So I'll introduce some hyperbolic models. The first is called the Poincare ball. The Poincare ball is just is a model with the Poincare ball model with radius 1 and a constant negative curvature -1 in n dimensions. Is the Riemannian manifold in fact, the D here is just the unit ball, where everyone is familiar with. It looks like just like a unit ball, but in fact, it's carried with a totally different Riemannian metric defined here. While the G subscript E here means the metric tensor in the Euclidean space, which is just an identity matrix. And this brings us a totally different distance function in this space. So this too might seem abstract, but let's see a figure here. So this is a Poincare ball, and let's first focus on figure A. While the L1, L2, L3, and the P1, P2, P3 are examples of lines in hyperbolic space, while L1, L2, and L3 intersect to form a triangle ABC, and we can see that the sum of its angles and small a plus small b plus small c is less than pi. And as opposite to Euclidean geometry, if we think of point C and the line 1, L1, and then the point C is not in L1, and there are infinitely many lines that are parallel to line L1 and go through a point C. In fact, P1, P2, P3 are all examples of such parallel lines, but we can find infinitely number of them. In figure B, in fact, all the triangles and heptagons are all of the same hyperbolic size, but the size of their Euclidean representations, if we view this figure in Euclidean space, we will find that, in fact, their size are decreasing in an exponential rate as a function of the radius from the center, and correspondingly, their number are increased exponentially. This sounds very strange in Euclidean space, but hyperbolic space is just have a structure like this, while in the center, it's something like its points are very sparse, but around the boundary they are very, very dense. So another well-known hyperbolic model is called a hyperbolic model. It's also called a Lorentz model or Minkowski model because it's defining the Minkowski space. So the hyperbolic model with I radius, and the I here means the complex number, and the constant negative curvature -1 in n dimensions is defined as this Riemannian manifold, where the H here, this seems very familiar, because if we think of this in 3-dimensional space, that means take n to be 3. That this is just means a negative x squared add y squared add z squared equals to -1. And this is just a hyperbolic, which everyone was familiar in analytical geometry. But of course, it's half of the hyperbolic. It's just the forward sheet of it. But it's not that completely the same with a hyperbolic, because the Riemannian metric here is different. The first element of it is -1 instead of 1. And to visualize it, so this is just because if we only think of the manifold, so it's just like a hyperbolic here, but remember the Riemannian metric is different. And these are corresponding to a mapping from the Poincare board to the hyperbolic model. While these, if we imagine we have a light here shooting from the point 0, -1, and this gives this, in fact, this proves that the Poincare board and the hyperbolic model, they are isomorphic. And then so that's the end of the math part. It's very long and boring, but it's very necessary. So let's then talk about hyperbolic geometry of complex networks. That means, why do we need to do graph machine learning in hyperbolic geometry? In fact, in Euclidean space, we all know that as the radius increases, the volume of an object exhibits a polynomial growth. For example, in two dimensions, the area of an object is like is proportional to the square of the radius, while in 3-dimensional it's proportional to the cubic of the radius. But however, if we think of a tree like hierarchical data, for example, see the figure on the right, the number of nodes is increasing exponentially with number of layers in the tree. So imagine if every node have two offsprings in the tree. So on the first layer, we have 1 node, and the second layer, we have 2 nodes, and the third layer, we have 4 nodes. So these number of nodes are increasing at exponential rate. So in this case, the Euclidean space becomes too narrow for tree-like graphs. Of course, there's a solution. We can just increasing the embedding dimensions, the embedding size. That means the dimension for the embedding. But because the right figure is just embedding a 2-dimensional, we can, for example, what do we make it for 10 dimension or 100 dimension? Of course, this will partially solve this problem, but in fact, the computational cost and the memory comes to an issue, and this is not very efficient. So people came to think that, what about another kind of non-Euclidean space, for example, hyperbolic space? In fact, from the figure here in the Poincare board, we can see sort of think that this volume of hyperbolic space, in fact, has an exponential growth, unlike Euclidean, which is polynomial rate. And in fact, from the table here, we can see the circle length and disk area of a hyperbolic ball on a Boyne hyperbolic space. In fact, they are all related to hypersine or hypercosine. So it's just the exponential rate here. So that means hyperbolic space has more capacity to embed this kind of tree-like graph, which has plenty more nodes in some higher layers of this node. And another problem is that if a tree is embedding a low-dimensional Euclidean space, serious distortion will occur. And this is the definition of distortion, but we won't talk about detail about that. But just see this graph. See the figure here. The red node and the green node, they are, in fact, the green node, the red node and the green node, they are very, very far apart in this tree. In fact, their graph distance should be 1, 2, 3, 4, 5, 6, 9, 8. They should be 8. But in a 2-dimensional embedding space, they are very close to each other, which gives us a very small embedding size. Give a very small distance in the embedding space. So this doesn't fit our definition of a good embedding. So this cannot give us a good embedding because this distance is small while they're far apart in the graph. So what about hyperbolic space? In fact, in hyperbolic space, the geodesics of 2 points, they are not straight lines. We mentioned just before, they could be curved. In fact, in hyperbolic space, it tends to like the geodesic here will bend towards the origin. So just like something like the black line here, but of course it won't just pass the origin, but it will bend towards here. So it can, in fact, it can give us a better approximation of the geodesics. The geodesics give us a better approximation of the graph distance here. So the tree-like graphs have a better representation in hyperbolic space than the Euclidean space. And then, so we can conclude that hyperbolic space is just like a continuous version of trees. And when we want to model data, choosing the different space implies different assumptions about the distribution of the data. In fact, people are model everything in the Euclidean space, and that's not the best choice because it seems like we just fix the curvature to be 0, but while in many cases the curvature should be another number. For example, for tree-like graph, we use a negative curvature, and if we have a circle-like graph, that means the graph has many circles. That in fact it's better to model the data in a sphere or something. And we have a quantity called hyperbolicity to reveal a network's closeness to tree structure. Its formula is given here, but we won't go much detail about that. And the low value of hyperbolicity means the graph is more tree-like. And in fact, most real-world graphs have a property called scale-free that's very similar to trees. This is very intuitive because imagine when you are creating a new web, you always want to link your web to some popular websites like Google or something, and you won't just randomly choose a web and link it to it, and your web no one will care about your web. So it's the scale-free property is in fact it means the degree distribution of the graph have a power law tail, which decays not that fast. So it allows the emergence of very large degree nodes. So that brings hierarchy structure in this graph.
Sicheng, I have a question on the hyperbolicity. So if you have a big data set,
yeah,
you can compute hyperbolicity for that data set, or if it's a homogeneous tree, I can understand it. One number will describe how hyperbolic, how high.
There's here I'm only given the definition, but there is also an algorithm to compute that.
Okay, but is it one number characterized all, or if it's in homogeneous?
Yeah, it characterizes all of the graph because all of the points in this metric space need to satisfy the 4-point condition.
Have you actually done that exercise? Have you computed the hyperbolicity for different data sets?
In fact, no.
Okay.
And so here, what I'm just talking about is that real-world graph is more likely to have a tree-like structure. And in contrast, if you do a synthetic graph like the well-known Adolph-Rhein random graph, it has a Poisson-like degree distribution. And Poisson distribution decays in an exponential tail, which means it's very unlikely that a node with a very large degree that will emerge. And so then let's talk about some algorithms. That means how to use our observations to develop some algorithm. That means hyperbolic embedding of graphs. The first work in this area is done by Maximilian Nickel. In fact, he has many great contributions in this area from Facebook AI. And in fact, the idea is very intuitive. We just want to change the embedding space to the Poincare ball in n dimensions. And we use the negative distance. Just to clarify, this must be hyperbolic distance. So just use the negative hyperbolic distance to characterize the similarity. So in this sense, the decoder is just like take 2 points in the hyperbolic space, and we're going to use negative hyperbolic distance to assign a similarity score to the embedding pairs. And intuitively, similar pairs should have a low hyperbolic distance, while this similar pair should be far away in the hyperbolic space. So in terms of loss functions, so the author proposed to adapt the skip-gram word-to-vec model to learn graph representations. And in fact, this is the same loss function when we are used in the word-to-vec in NLP. So basically, the numerator term here in the loss, we are trying to pull connected pair closer together, while the denominator will push negative pairs apart in the hyperbolic space. And this can be interpreted as a soft ranking loss. And usually the negative examples are too many for node U. That means for nodes that are not connected with V, that there are too many. So here it's common to approximate the denominator with a trick called negative sampling. And this is very straightforward, but we are not that. But we are still missing one key component, which is the optimization algorithm. And when we talk about this in the Euclidean space, we can just apply the gradient descent steps by following the Euclidean geodesic, which is just a straight line. And so here we need to adapt this algorithm to account for the structure of the hyperbolic space, or more generally on Riemannian manifold. So this is an algorithm called Riemannian stochastic gradient descent, and this is proposed by some authors in 2013. So its algorithm is just like, it starts by computing Euclidean gradients, and we rescale them by the inverse metric tensor here to account for the Riemannian structure of this space, and then project this result on the tangent space to get the Riemannian gradient. So here we can just think of that the Riemannian gradient is just a rescaled Euclidean gradient, but not that simple. In fact, it's a metric, it's a tensor on the, it's a tangent vector on the tangent space. And the last step is to apply the gradient update. So in Euclidean stochastic gradient descent, the update is just to add the gradient times the learning rate, but we don't have a notation. We don't have a notion of a vector addition in Riemannian manifolds. But we do have a similar concept, which is the exponential map. We just mentioned it's a map that maps from the tangent space to the original manifold. So Riemannian SGD use the exponential map to map Riemannian gradients, which are basically tangent vectors onto that manifold. And in contrast with the Euclidean gradient descent, which follows straight line geodesics, the Riemannian gradient is going to follow a curved line geodesics. And here is where the exponential map comes to use. And often in practice, because we know the existence of the exponential map, but for many complicated Riemannian geometries, we don't have a formula for exponential map. Of course, you can get it if you want. For example, you can to compute the geodesics, you need to solve an Euler Lagrange equation, and that will be not very easy. But I mean, for some simple, for some common Riemannian geometry models, we have a formula for the exponential map, but not for every model. So for these models that don't have a closed form exponential map, we need to do approximation. Here, the first order approximation of the exponential map is called the retraction operator. And sometimes we will just use the restriction operator to do Riemannian gradient descent. And here, if we apply all these tricks we mentioned before about Riemannian stochastic gradient descent, and here's the closed form of the RSGD in the Poincare embedding task. And the projection here is just if theta goes beyond the Poincare ball, we just map it back. to ensure that its radius is less than 1. Now here's the result. So the task the author was using it. They are using the transitivity closure in the WordNet, and they do 2-dimensional Poincare embeddings of the WordNet mammal subtree. And the left one is the intermediate embedding after 20 epochs of the hyperbolic embedding, and the figure B is just a well-trained embedding. Well, we can see that here the word mammal are in the center of this Poincare ball, while some words should be in the low hierarchy. For example, cats and tigers and elephants. Here, elephants or something. They are nearly to the boundary. So that means it captures the hierarchy very well. In fact, there are some 2 videos here. I don't know if I should share it. So let's see if I can share. So can you see the video here?
Yes.
Yeah. Okay. So this is the training process of the hyperbolic embedding, where we can see as the epoch goes larger and larger, the embedding just become more and more clear, and there are clearly means these embedding are capturing the hierarchy of this data set. While for another one, this is the Euclidean. So can you still see the screen?
Yeah.
Yeah, this is for the Euclidean embedding, but we can find that the Euclidean embedding is a little bit chaotic when they're organized in space. Some its leaves are close to the roots or close to another leaves or close to another branch of the tree. So in some sense, it fails to capture the hierarchy. But in hyperbolic space, the things are get much better. Different branches are entangled very well. Like this might give us an intuition why we can do a better embedding in hyperbolic space for hierarchical data. And they also do some experiment on the WordNet, and they use 2 different tasks to evaluate the embedding. The first is reconstruction task. Next one is link prediction, and we can see the result here is very good. For Euclidean embedding, and the translational embedding is just a variant of Euclidean. It's still in Euclidean space. And here, in Euclidean embedding, if we use embedding in 200-dimensional space, it cannot beat the hyperbolic embedding in 5-dimensional space, and that's much better. And also for the link prediction task. In fact, the reconstruction task illustrate that indeed the hyperbolic space has more capacity for the tree-like hierarchical graph, and the link prediction task illustrates that embedding in hyperbolic space did have the greater generalization property. So then this part I'll just make it quick because everything is more similar. This is called Laurent's embedding, and this is also proposed by McMillan Nicol. So in fact, everything was the same. Just they changed it from the Poincare ball to the Laurent's model, or we are saying the hyperbolic model. And the loss function is the same. Only the distance here is changed from the distance in the Laurent's model, and here is the stochastic gradient descent. But a difference is that in the Laurent's model, formulas becomes more simple, and we have a closed form for the exponential map. So we do not need to do a retraction approximation to the exponential map. And this is kind of called the fully Riemannian stochastic gradient descent. And in fact, the results, the author also evaluate these embeddings on taxonomy embeddings, also on WordNet. But we can see they claim that the Laurent's can get a better result than Poincare ball. So this brings us to a question: is that which hyperbolic model we should choose? We should choose Poincare ball or Laurent's model. In fact, there are both very commonly used in the area of hyperbolic learning, but we can find majority of the research in the literature is based on the Poincare ball. But in fact, the most advantage of the Lorentz model is that it has better numerical stabilities, because in fact, if we see this graph, see this figure here, when the embeddings are close to boundary, these are very close. These points get very close to together, and sometimes the machine precision is not enough to represent this difference from these different embeddings. So in practice, Lorentz model gives a better numerical instability. But in fact, the Lorentz model have a poor problem that it's unbounded. It's not and its constraint. Its constraint is like we need the Lorentz product of two vectors to be -1, and equality constraint is much more difficult than inequality constraint to preserve in optimization. So it is open to discussion whether which model are better, but they are all very popular in this area. Also, the Poincare ball has an advantage that it's very easy to visualize because it's a ball, right? Okay. So when some researchers doing research in the hyperbolic model, they also projected to the Poincare ball to see the results, visualize the result, and we can see the hierarchy. So the next topic and the last topic would be the neural networks in hyperbolic space, because so far what we talk about is just embeddings, and in fact they are very shallow embeddings and cannot be generalized to unseen graphs or something. So the first question would be, how would we use hyperbolic embeddings in downstream tasks? Because we have claimed that we have an embedding, and how to use it is we want to use the embeddings to do link prediction or classification or something. And so it's very straightforward to think we can just feed them into a traditional neural network. But of course we can do it, but theoretically this is not appropriate, because we are totally ignoring the hyperbolic geometry in that embedding. Of course, many people claim that we have a neural network, and neural network can learn everything. So the hyperbolic geometry, the mapping from hyperbolic geometry to Euclidean geometry, they are learned in a neural network. But in fact, it's not appropriate, and mathematically speaking, it's not true to just feed these embeddings in hyperbolic space to a traditional neural network in Euclidean space. So that problem becomes, how do we construct a neural network in hyperbolic space? And in fact, this is a very mathematically challenging task, because we don't have an algebraic structure on hyperbolic space yet. What we have talking about, like distance, like geodesics, like tangent space, these are topological structures. So what means by algebraic structure? That means we don't have basic operations on hyperbolic space. For example, we don't know what does it mean for two vectors added together. In fact, there are two cases. There are two approaches to handle this. The first is just approximate the basic operations in hyperbolic space using tangent space, because we are saying any manifold is locally Euclidean. So locally means around a point on the manifold. So if we see on the neighborhood of that point, we can use tangent space to approximate the operations in hyperbolic space. And the tangent space is Euclidean, so we can just use everything we are familiar with. And of course, this is approximation. This is not the perfect solution. And another way is called the gyro vector space. So a gyro vector space is it provides an elegant non-associative algebraic formula for hyperbolic geometry. It's just like the role of linear space or vector space in Euclidean geometry. So, but the operations in this are not very not as simple as what we are familiar with in Euclidean geometry. For example, if we denote the generalized Poincare ball, that with curvature minus c, and the radius here is just square root of c over 1. And here for 2 points that in the generalized Poincare ball, then we define the Mobius addition as here. And here, while the angle pairedness and the norm here, they are just Euclidean norm and computing in Euclidean way. And here the Mobius scalar multiplication, while R is a number and X is a point in the generalized Poincare ball. Many people will raise a question like, why do we need to do this? That why we just like add them together like X add Y, like what we do in Euclidean space. In fact, there's a much more, there's a very intuitive example if you are familiar with the general relativity, because we know in the framework of relativity, no speed can exceed the speed of light. But in fact, if you are doing something like we have 2 speed vectors and they are all close to the speed of light. If you just add them in the Euclidean space, and definitely it will exceed the speed of light, and that's not allowed in general relativity. So so if you are talking about general relativity within the framework of Riemannian geometry, that's the Mobius addition in gyro vector space. While in preliminary relativity, this is called Lorentz transform. And so that means we have two, if say mathematically, we have 2 vectors on the hyperbolic manifold. To add them together, we need to ensure that the addition is still in the hyperbolic space. It cannot go out of the manifold. So we need to define something special like the Mobius addition and Mobius scalar multiplication. And then we have defined the, yeah.
Hi, Sicheng, this is Jen. I have a quick question regarding your previous slide. Like, do you have this kind of addition and multiplication formula also for the Lorentz space that you were talking about, or is just for the Poincare balls?
In fact, for different space, they are all isomorphic, but their formulas are totally different.
Okay, so
and in fact, the use of this kind of algebraic structures, later we'll see that we can derive some closed form formulas based on this kind of basic operations. But as I mentioned before, on Lorentz model, naturally we have many like closed form formulas for exponential map or something, but in Poincare ball we don't have such things, so we need an algebraic structure to obtain a formula for it.
Yeah, that makes sense. Thank you.
Okay. And then, so based on these kind of operations, the addition and multiplication, we have some closed form formulas for many quantities like distance, geodesics, and exponential and logarithm map. And these are within the framework with the Poincare ball. And while before we are talking about Poincare embedding, we see that we don't have any formulas of the exponential map, and we need to do a retraction approximation of it, and the parallel transport. And in fact, we can claim that neural networks are just the composition of these kind of operations, these basic operations, although their formula is very complicated. Like we have point-wise nonlinearities, and we have matrix vector multiplication, and we have bias translation. It's just addition here, and have vector concatenation or something. And with these kind of formulas, we are ready to define the neural network in hyperbolic space. And in fact, something like hyperbolic softmax regression, hyperbolic fit-forward layers, hyperbolic recurrent neural networks, and mathematically they have very complicated formulas, and I won't talk to any details about that. So if you are interested in it, you can see this paper in Neuros 2018 called Hyperbolic Neural Networks. And so these are the results in that paper. So so the author just proposed that if they feed a hyperbolic embedding in different to different in different networks, and they tried hyperbolic neural network and Euclidean, the standard Euclidean network. And the last thing is that they first project the hyperbolic space by logarithm map to the tangent space and use the Euclidean neural network. And we can see that the hyperbolic neural network in all cases is doing a good job. But for large dimensions like 10 here, their difference is not that big. And in fact, it's a very common observation in the field of hyperbolic learning that in very small dimensions like d equals to 2 or d equals to 5, and hyperbolic embedding have very great advantage to more hierarchical models. But if the dimension go large, that advantage will finally disappear there, because the difference of Euclidean and hyperbolic is not that much. And the last thing I will talk about is about hyperbolic graph convolutional neural networks. Because the hyperbolic embedding methods I have talked about, they are all transductive methods. That means we can only pre-compute an embedding and we want to use it. We just take any node, and just like a hash table, we just find the corresponding embedding and we use it. And these embeddings, they only capture the graph structure. They make use of the node features. And of course, the node features are in Euclidean space. And these Kannabiran method also has bad scalability, because if your nodes are growing and the size of the total size of the embedding will grow linearly with that with the number of nodes, and that means for a very large graph we need a very large embedding, so it doesn't have a good scalability. So we'd like to extend the inductive method, especially that means graph neural networks, to hyperbolic space. But in fact, it's not like a easy work, because there are many challenges. For example, as I mentioned before, the input features are usually Euclidean, and of course we can map it to the hyperbolic space. And something more difficult is like we need to perform the message computing and the aggregation procedure in the hyperbolic space, which is usually just conducted in the Euclidean space. And we don't know how what is the right amount of curvature for the hyperbolic space that can perfectly embed the graph. So in this work, the author, they proposed the HGCN, that's called hyperbolic graph convolutional neural networks. And they use the Lorentz model as the embedding space. And to address the third challenge I was mentioned before, they make the curvature at each layer learnable. So it's not like what I'm talking before, that everything was fixed, every curvature is fixed to -1. Here, the curvature is learnable. And first, they map the input Euclidean features to hyperbolic space, and do some the linear transformation in the hyperbolic space is obtained by first map to tangent space and apply the transformation in the tangent space, then map back to the manifold. So they are not using a gyro vector space. They are just doing a first order approximation by tangent space. That's the first way I talked before to cope with the operation on the hyperbolic space. And then neighborhood aggregation. So for aggregation, the author used attention-based aggregation, and also the attention was done in the tangent space. In fact, in the paper, they also claim that why they would use a tangent space, despite except that the attention itself is a very great mechanism for aggregation, because in graph neural networks, typically people would do something like mean aggregation or maximum aggregation, but mean, in fact, in hyperbolic space is much more difficult to define. It's not like just adding every coordinate and divide them by the total number and just get the mean. And this is also not correct in hyperbolic space. So they use an attention-based aggregation. And the nonlinear activation is also done in hyperbolic space. but here a little bit different because different layers are with different curvatures. So the nonlinear activation also is not the same. So this is this figure just this outline of the HGCN structure, while the neighborhood aggregation is first maps messengers and embedding to the tangent space, which are in the middle here. We can see the green point in the center is the node information we want to aggregate. And after aggregated, we just pointed to another hyperbolic space and with totally different curvature. It's a new space. And these are a comparison of the GCN and HGCN. You can see that everything is almost the same, except that every basic operation here, we are changing them to the hyperbolic space. These are hyperbolic matrix vector multiplication, and this is hyperbolic addition. And another distinction is that here the aggregation was changed to attention-based, and the nonlinear activation is in different space with different curvatures. So in fact, although these functions seems very complex, they are all differentiable. So we can still use similar what we done similar to for example, you can implement it in TensorFlow or PyTorch and do optimization like Riemannian stochastic gradient descent to do this to finish the training. So finally, just to show a bit of results, here we can see a GN embedding of a tree-like structure. This is a visualization of for the link prediction on the diseases dataset and node classification or the Cora dataset. The figure A shows that this is the first layer and the last layer for the diseases dataset. And here we can, from the table, we can see that the disease dataset had the hyperbolicity equals to 0. That means it's very, it has a structure that's very similar like tree. But for GCN layers, it cannot capture the node hierarchies very perfectly. While in HGCN layers, this is the first layer and the last layer, we can see that HGCN is preserve the node hierarchies very good. And also, the figure C is a Cora dataset, but the Cora dataset has a hyperbolicity of 11. It's a very large hyperbolicity, which means it doesn't look like graph. And as we can see that in the Cora dataset, from the table, the HGCN, it doesn't have the best result among all these datasets. In fact, in this dataset, the graph attention networks did the best. And although they didn't get a good result, on the Cora node classification task, we can find that the HGCN can lead to a better separation. That if you see the figure C on the right, you can see the embedding produced by HGCN on Cora dataset. They are almost linearly separable. So that means HGCN did give a good job in some sense. So in the hyperbolic GCN, we are able to recover some tree-like structure very nicely, and all the points are embedded in their respective hierarchy. And to summarize, hyperbolic space can be regarded as a continuous tree, so make it very well suited for modeling datasets with hierarchy. And also, hyperbolic learning has achieved great success in graph data, especially with tree-like structure. So I presented some models and algorithms about hyperbolic graph neural networks, and along with some applications around machine learning tasks on several data sets. And so there are many opportunities and many new challenges in this field. For example, the challenges is like all the operations mentioned in this is much more difficult than the standard one in the Euclidean space, and also the coding is much more difficult. And but indeed, there are many this also brings some numerous opportunities. So there are many also researchers engaged in this field. And so this is the end of my presentation. So if you'd like to learn more about hyperbolic embeddings and related machine learning tasks, you can check out the open source repos here in the GitHub. And someone just have a good summary about it. And thank you for listening.
Thank you, Sicheng. That was amazing. Do we have questions?
Sicheng, can you say something about the hyperbolic graph, convolutional graph networks? Has everything that's been published so far is all on classification, or are there papers on regression too?
I don't think it's many on regression. There's also another paper on the graph classification task, but because this paper is focused on node classification and leak prediction.
Right.
And I don't think the whole graph machine learning community focuses on some regression tasks, in fact.
Because it's the accuracy of classification is actually spectacular, especially if delta is small. So, so they're very powerful, as you said, in low dimensions, which. So what kind of applications are these? Just this table one has all the applications published, or are there more out there?
You mean for different data set or different?
Yeah, different data set, different tasks, different applications, different domains.
No, this is just from the HGCM paper, not from a review paper or something.
Right. So these are standard benchmark. I recognize Cora and okay.
Yeah.
PubMed, yeah. When do I know that the data? What is delta? I know delta has to go to 0, but it's never 0. How do I know? Like at the airport, I would think there is some hierarchy, but delta equals 1, or the PubMed, delta equals 3.5 or 11. Where is the threshold where I say, okay, now I have, in this data set, I have a hierarchical tree, and therefore hyperbolic graph embedding may make sense. Do you know what is the cutoff?
In fact, the author didn't mention. I suppose it also should be something like it's a relative quantity, not very absolutely one.
So it depends on the application, you mean?
Yeah.
Okay.
Do we have more questions for Sicheng? So if there are no more questions, we come to an end of our of this week's Grant seminar. And everybody have a great weekend and a great rest of the day. Thank you.
Thanks, Samdata. Thanks, everyone. Thanks for coming. Bye-bye.
Bye-bye.